Okay, welcome back. This is COL 774 Machine Learning, May 2nd, 2020. Today is a Saturday, and I just thought that I will take an extra class or an early class so that we can complete the material. This will be our last class for the course. So remember, previous class we were looking at learning theory. Specifically, we started this topic or concept on VC dimension, that is Vapnik, Charbon, and Kiss dimension, which is named after Russian mathematicians who invented this concept, right? And recall that also this was primarily motivated to talk about hypothesis classes or hypothesis spaces which are infinite dimensional, right? We did not have a way to develop pack learning theory, right, for hypothesis classes which are infinite dimensional, right? And therefore we said this theory we will develop this theory of VC dimension, which probably will help us give pack learning bounds for hypothesis classes, right, which are infinite dimensional, and many interesting cases fall in there, right? And let me sort of recall or just revisit the examples that we considered last time. So this is with respect to shattering, right? This is a concept that we introduced, and recall that shattering is defined, right, given an instance space and a set of points S, right? So I'm looking at the right side of the slide in the blue, right? So given an instance space X and a set of point S, which uh, which belong to that instance space X, we say that a hypothesis class H, right, this curly H shatters the set of points in this set S if for any possible labeling that you could give to the points in the set S, right, there is a corresponding hypothesis belonging to the hypothesis class which can achieve that labeling, right? For right, let's take this specific example. I should also mention that in the last class, I think there was a slight mistake on one of the slides, where in this 2D example, where we had 3 points, I might have said the number of labelings is 2 to the 8, but it's actually 2 to the 3, right? So there are 8 possible combinations of positives and negatives, right, which can be assigned to these 3 points, right? So given these 3 points, right, there are 8 possible labelings, and the question is, for each of these possible labelings, right, is there a hypothesis, right, for example, in the linear hypothesis class in 2D, right, which can achieve this labeling, right? For example, if two of the points are positive on the top and the lower one is negative, then there is a line which separates them, right? And this particular classifier can classify the ones above as positive and the one below as negative, right? So there exists a hypothesis which achieves this labeling, and if we can do this, right, for sort of every possible labeling of these points, then we say the set of points is shattered, right? And we also talked about this doing this in an adversarial setting, where adversary gives us a labeling for a given set of points, and we try to find out a hypothesis which achieves that labeling, and right, adversary gives us another labeling, and we try to find a hypothesis which achieves or realizes this labeling, and so on and so forth. And if we can do this for every possible labeling that the adversary gives for a given fixed set of points, then we say the points are shattered. Okay. And then finally, right, in the end of the last class, we gave the definition of VC dimension, which was for a given hypothesis space, or let me use the word class, hypothesis class H, right? And this is with respect to an instance space X over which H operates in some sense, right? The VC dimension of H is nothing but the size of the largest set S that can be shattered by H, right? So I'll repeat it, right? So the VC dimension of a hypothesis class is simply the size of the largest set S that can be shattered by H, right? And we'll look at it in sort of ground it more in the next slide. So the top of this slide just repeats the definition of VC dimension of hypothesis class, right? Given a hypothesis class H, right, curly H defined over an instance space X, curly X, VC dimension of H is simply defined to be the size of the largest set S, right, which is a subset of the instance space X, such that S can be shattered by H, right? So let us look at the example that you were looking at in the previous slide, right? And this is the hypothesis class of all linear classifiers in 2D, right? And in the previous slide, we showed that there was a set of points, right, of size 3, right, which can be shattered by this hypothesis class. And note that in this definition, right, if you look at it carefully, we are simply saying that for the VC dimension to be, let's say D, right, there has to be some set of points, right, of size D which can be shattered, right? So this sum is very, very important, because we are saying that it is not that every set of that size D should be shattered. It is simply saying that there has to exist some set of that size that should be shattered, and then we can say the VC dimension is at least that much, right? At least, let's say D. In this case, the D is 3, right? So if you look at the right side of this slide, right, where we say VC dimension of this hypothesis class is 3, right? So to prove that, right, the first thing that will prove is that there exists a set S, right? There exists is very important, right, of size 3, right, which is a subset of the instance space, such that S can be shattered by H, right? So there has to be some set of that size which can be shattered, and that we showed in the previous slide, right, that there was a set of 3 points which can be shattered, and that is sufficient to prove that VC dimension is at least D, or D is equal to 3 in this case, right? But the second condition says that to prove that the VC dimension is exactly equal to D, or 3 in this particular case, right, we have to also be able to prove that it is not more than 3, right? And that's where is the trick sort of lies, because that's slightly more difficult to prove in general. And why is that? Right, let us look at this example, right? But before even actually we can go to the example, right, look at the definition again, right? Because we are saying VC dimension is the size of the largest set S which can be shattered by this hypothesis class, right? To be able to show that this is exactly equal to 3, we have to show that there is no set of size 4 or more, right? So more than D, right? If we are proving that the VC dimension is D, right, then we have to be able to show that there is no set of size D plus 1 or more, right, which can be shattered, right? So this, right, so therefore this is sort of for all condition, right? Or it is saying that for all sets of size 4 or more, right, they cannot be shattered. Another way to write that condition is there does not exist a set of size there does not exist a set S of size 4 such that it can be shattered. Right, in this case, note that I'll just come to the specific example, but note that we will prove that there is no set of size 4 which can be shattered, and it is sort of a trivial or very simple exercise to show that if there is no set of size 4 which can be shattered, then it is not very difficult to show that there is no set of size more than 4 which can be shattered, right? So this is an exercise I will leave as homework for you to prove that if there is no set of size 4 that can be shattered, then there is no set of size more than 4 that can be shattered, right? So and similarly for D plus 1 and more than D plus 1 in general, but I will come to that general case very soon. But let us look at this example now again, that we have shown that there is a set of size 3 which can be shattered. So the first condition is sort of proved in this case. The second condition is that there is no set of size 4 which can be shattered, and to prove this we have to use some kind of combinatorial or some sort of argument which exploits the structure of the problem, right? So presumably, because we cannot really enumerate all possible sets of size 4, right, because there are infinite number of them, right? And that's where right, and that's where uh, uh, right, in that context, just let us look at this example, right? So what we have to prove now is that there is no set of 4 points which can be shattered. But let's look at this particular example just to get the intuition how we will prove it for this particular case, right? So we will say that, suppose you are given some set of 4 points x1, x2, x3, x4, right? And right, they could be in any sort of fashion, but let's just look at this specific arrangement where they are on four sort of corners of some kind of four side uh, um, polygon, right? And what we will do is that we will label sort of opposite points, right, as positive, right, and on one diagonal, right, which is x1 and x4 in this case, and the 2 points on the other diagonal, right, if you will, as negative, right? and it is not very difficult to show, right? And this is very similar to the XOR case that we had seen um, earlier, uh, right, in the context of neural networks, that there is no linear separator which can actually achieve this labeling, where these opposite points are labeled as positive, and the other 2 points, which is x3 and x2 in this case, are labeled negative, right? And right, this is of course an argument for these specific four set of points, and that's why I said consider some kind of polygon, four uh, sided polygon, right, on which these points can be placed, right? And right, if you think about it carefully, right, whatever is the arrangement of points in the 2D space, you could make a similar argument, right? What will happen is that if they have a very specific structure, let's say if three or all of the points are collinear, then maybe you have to make a slightly different argument, but in most other cases this kind of polygon argument will work, right? But what is important is that, right, whatever we have done here is not really a complete proof, right? Because we have just given an intuition, right, how you will do it, and then sort of shown it for this particular sort of points, but trying right, have given sort of an intuition that works for the example that we see here, but this is not tied to the specific arrangement, right? I mean, this is a general argument that we're trying to make, that whatever is the 4 point arrangement in the 2D space, right, if you label sort of opposite points on a diagonal as positive and other set of opposite points as negative, then there is no linear hypothesis which can achieve this labeling, right? And a more formal argument will consider all possible such cases, right, of 4 points, which will include 3 being collinear or 4 being collinear. But once you make these cases, right, and you sort of make a more argument about the structure of these 4 points in general, right, then you can actually show that that VC dimension of this space is exactly equal to 3, because there is no set of 4 points which can be shattered by this hypothesis class, right? And in the next slide, we will actually make it slightly more general, for the case of general hypothesis classes, where we want to show that the VC dimension is exactly equal to D. So this is the more general case, right? That given an instance space X, curly X, and a hypothesis class H, right, to show that the VC dimension of curly H is equal to D, and this is the D that I was talking about in the previous slide. Maybe I should have written it explicitly, that D being referred to was actually the dimension of H, where D was 3 in the previous example. But in general, right, to be able to show that VC dimension of a hypothesis class H for a instance space X is D, right, we have to be able to show two things. First, that there is a set of size S, there is a set S of size D, right, which is a subset of the instance space, such that S can be shattered. So there has to be some set of size D which can be shattered, right? So this is the first condition, and typically this is not very difficult to prove, because we have to find some set of that size which can be shattered. But the second condition which we require is slightly more difficult to prove in general, is that there should be no set of size b plus 1, right, which can be shattered, uh, right? So there should not be any S, a subset of the instance space which is of size d plus 1, which can be shattered. And if we can show both of these conditions, then we can show the VC dimension is exactly equal to D, right? Once again, a remark about the second point, right? Being able to show that there is no set of size d plus 1, we have to make a more general argument, because we can't really sort of enumerate all possible sets of size d plus 1 in general, right? And this will be an argument of the nature that we made on the previous slide, right, in the example where we showed that no set of size 4 can be shattered in the 2D space by a set of linear hypothesis, by the linear hypothesis class, right? And as I stated in the previous slide, right, it is also important to note that it is sufficient to show that there is no set of size d plus 1 which can be shattered, to prove that VC dimension is exactly equal to D. I mean, showing condition A and condition B is sufficient to show that VC dimension is exactly equal to D, because, right, if condition B is satisfied, that there is no set of size d plus 1, as an homework exercise, right, you should prove that there cannot exist a set of size more than d plus 1 which can be shattered. And therefore, right, these two conditions together show us, or prove that D is the size of the largest set, right, which can be shattered by the hypothesis class H, and therefore the VC dimension is exactly equal to D, right? So this is sort of the nature of a more general argument. So now let us look at another hypothesis class in the 2D space, right, which is in some sense more powerful, right? Or we'll see that the VC dimension of this hypothesis class is strictly more than the VC dimension of linear classifiers in the 2D space, right? So here, right, look at the right. So in R2, right, let's say H is the set of all linear separators or linear classifiers, and H prime is a new hypothesis class, which is the set of all quadratic separators, right? And we'll sort of try to argue that the VC dimension of H prime, which is the set of all quadratic separators, is more than the VC dimension of H, which is the set of all linear separators, right? And recall that we have already shown that the VC dimension of H is exactly equal to 3, right? Now, how do we show that the VC dimension of the quadratic separators is more than 3, right? It's not very difficult to show this in this case, because what we have to show is simply that there is a set of size 4 in the 2D space which can be shattered by the quadratic classifiers and will be done, right? Right, because we have to show that there is some set of size 4 which can be shattered, right? And um, so let us look at this particular arrangement of the points, right? X1, X2, X3, and X4, right, on the 2D plane, right? This is some set of arrangement of points, right? And we'll show that this particular arrangement or this particular set of points can be shattered by a quadratic classifier, right? And recall that in some sense the most difficult case, right, for shattering these set of 4 points, right, which led us to a sort of stumbling block in the case of linear classifiers was when these opposite points were labeled positive, right? So x1 and x3 are labeled positive and x2 and x4 are labeled negative, and a linear classifier, any linear classifier, could not really achieve that labeling, right? But it is not difficult to show, or in fact it's a very simple argument, that a quadratic classifier exists which can achieve this labeling. For example, what we can do simply is construct a ellipse around these points x1 and x3, right? So construct this ellipse which is sort of shown in the red, right, around x1 and x3, right, which are labeled as positive, right, and and anything outside that ellipse, right, which is sort of a quadratic boundary, will be negative, right? And right, this is for this particular case, right? But we could also look at the cases, right, which is sort of in the green, right? So this is right, one particular assignment where x1 and x3 are positive, and x2 and x4 are negative. But we can also look at the case, right, which is sort of covered by this green ellipse, that when x2 and x4 are positive, like, right, labeled in the green, and x1 and x3 are negative, right, then we can use this green sort of classifier to achieve this labeling, right? And if you think about it, right, although there are 16 possible labelings, right, this is sort of the most difficult case where the opposite points are labeled positive and other are labeled negative, and these sort of more difficult cases are covered by this example, and the other examples are not very difficult to right, or rather other labelings are not very difficult to achieve, right? In fact, they can also be achieved by linear classifier. For example, right, if we label x1, x2, and x4 as positive, then this purple linear classifier itself will be able to achieve that labeling, right? And we can show in general that all 16 possible labelings can be achieved by these quadratic classifiers of this set of 4 points, right? Therefore, we have sort of made an argument that in fact the VC dimension of this quadratic classifier into the space is at least 4, right? Now the interesting question is it exactly 4? And I guess the answer, I think, is no. Right, there is probably a formula which lets you compute the VC dimension of arbitrary sort of degree polynomials in let's say in 2D space, or in high dimensional space, but maybe that's something separately I will share. But what we have shown here on this slide is definitely that the quadratic classifier, the VC dimension in 2D space, is at least 4, which also means that in some sense they are more powerful, right? And we'll talk about that in one of the later slides than linear classifiers, and this will lead us to two interesting results about backbound, right, using this notion of VC dimension. Just to make it very clear, right, when we say set of quadratic classifiers in this space, this is simply h theta of x, where x is some point in the 2D space x1, x2. This is simply the indicator of theta t2 theta 2 2 x2 square plus theta 1 1 x1 square plus theta 1 2 x1 x2 theta 2 x2 theta 1 x1 plus theta 0 greater than equal to 0, right? So this is sort of a natural extension of the linear classifier where these thetas are the parameters of the hypothesis, right? And we get different hypotheses for different values of theta, and the space spanned by these kinds of hypotheses in the 2D space is the set of quadratic classifiers, and the ellipses that we have sort of argued above in this example are specific instances of these quadratic classifiers. Okay, let's move on to the next slide. Okay, so I will now do couple of more examples, right, of computing VC dimension of different kind of hypothesis classes, right, and in 2D, and in fact in case of 1D space, right, I guess more detailed sort of uh, example in the 2D space, right, just to give you more feel, a better feel of how do we really deal with this problem of computing this dimension, right? So consider again the instance space being R2, right, a two-dimensional Euclidean space, and let's say your hypothesis class is simply the set of all axis parallel rectangles, right? So all rectangles, right, whose axes are sort of parallel to sort of x or y axis, right, or sort of x1 and x2 axis, right, in the case where we use x1 for one sort of one dimension and x2 for the second dimension, right? And what is the hypothesis, right, which belong to this class is simply, right, given these hypotheses which are in the form of this rectangle, right, we will simply say that a point belongs to or rather a point is classified as one by a particular hypothesis if x lies inside that rectangle defined by h, right, and zero otherwise, right? And how do we really define these rectangles, right? You can think of these as sort of the parameters, right, which specify a particular hypothesis in this hypothesis class, right? So we have two sets of points, which determine a hypothesis, right? So this is alpha beta and alpha prime beta prime, right? So think of these 2 points, right, as sort of the opposite sort of sides of the rectangle, right, that is defining this particular hypothesis. For example, alpha beta is on one end of the diagonal and alpha prime beta prime is on the other end of the diagonal, right? So this is our semantics. Remember that how we are defining this hypothesis, right, given, right, each hypothesis is defined in terms of these 2 points, right? The first point has coordinates alpha beta, and the second point has coordinate alpha prime and beta prime, and the way we construct this rectangle is simply considering these points as opposite ends sort of a diagonal, and then just construct the rectangle, right? And then you can right, see that this always defines a sort of a unique rectangle in the 2D space, right? And now, right, so given this hypothesis class, right, we will show that the VC dimension of this hypothesis class, right, where, right, given the hypothesis class which represents this rectangle, and a point is classified as 1 if it is inside this rectangle and 0 otherwise, right? So given this hypothesis class, we will show that the VC dimension of this hypothesis class in the 2D space is exactly equal to 4. Okay, and right, so as expected we will do this in 2 steps, right, showing that the VC dimension of this hypothesis class of the set of axis parallel rectangles in the 2D space is 4, right? We will do this, prove this in 2 steps, right, as expected. So the first step would be to show that the VC dimension is at least 4, right? And that's sort of the easy part in some sense, because we have to find some set of 4 points in the 2D space which can be shattered by this particular hypothesis class, right? So the particular set of 4 points that we draw here is simply this x1, x2, x3, and x4, the way I've written here, right? And again, I'll write there are 16 possible labelings, and we have to be able to show that for each possible labeling of these 4 points, right, arranged as above, right, there is a rectangle which sort of right, separates positives from negatives, right? And again, if you think about it, the slightly more difficult sort of labelings in this case are those, right, similar to the previous example, where opposite points are labeled positive, and the remaining opposite points, right, are labeled negative, right? For example, in this case, x1 and x4 are positive, and let's say x2 and x3 are negative, right? And in this case, right, the way to achieve this labeling would be simply to draw a rectangle around x1 and x4, right? So because they are inside this rectangle, so they are labeled positive, right? This particular labeling is shown in the red, right? So x1 and x4 are positive, and you draw this red rectangle, and x2 and x3 are shown negative in the red, right? So this particular labeling can be achieved, right? Similarly, right, analogously, right, if we label x2 and x3 as positive and x1 and x4 as negative, which is shown in the purple, again there is a rectangle around x2 and x3 which can achieve that labeling, right? And uh, right, so these sort of opposite uh, diagonal points being labeled same, and other diagonal point being labeled uh, otherwise is considered by this particular two rectangles, right? And there are other arrangements, for example, which is in green, right? x2 and x1 are positive, right, and x4 and x3 are negative, but this can be achieved by this green rectangle, right? And right, in fact, you can argue, or right, that there is exactly six possible sort of labelings which assign uh, 2 points, right, any 2 points among these as positive, and other two as negative, right? So there are sort of six possible combinations, and for each one of them, right, we can cover right, or we can achieve those labelings using an argument which is very similar to the one shown here, right? And among remaining cases, one is all positive, which is very simple to achieve because I can just draw a rectangle around all of these points. One is all negative, I can just draw a rectangle outside all these points, a rectangle which does not contain any of these points, right? That will be achieving all negative labeling, right? And what remains is I think eight labelings where right, four of them are where 3 points are labeled positive, one as negative, and it's not very difficult to show that there is a rectangle which classifies 3 points as positive. Just draw the rectangle around them and leave the fourth point, right? So there are four such cases, and finally four cases are where 4 points are labeled negative and 1 point is labeled as positive, and then you just draw a rectangle around the positive point in each of these four cases, right? And that sort of completes all possible 16 labelings of these 4 points, and we have sort of argued that these uh, 16 possible labelings can be achieved by some rectangle in the hypothesis space. Therefore, right, there is a set of size 4 which can be shattered by this hypothesis class, and therefore VC dimension is at least 4, right? And the next part of the proof would be to show that VC, to be able to show that VC dimension is exactly 4, we have to show that there is no set of 5 points in the R2 space which can be shattered by this hypothesis class, and we'll make that argument on the next slide. Okay, let us continue from the argument made on the previous slide, right? So the part A here on top left is simply repeating, right? We have already discussed that on the previous slide, which is right, that there is a set of 4 points which can be shattered, and this is simply showing that these are x1, x2, x3, and x4, right? And right, we have discussed this, right, that x1 and x3 being positive, right, and x2 and x4 being negative, shown in the blue, can be covered by this blue rectangle. Similarly, the labeling where x2 and x4 are positive and x1 and x3 are negative, shown by these green sort of markings, can be covered by this green rectangle, and so on and so forth, right? So but we have made that argument on the previous slide, right, that the VC dimension of this particular hypothesis class is at least 4, because this can be this set of 4 points can be shattered. But now let us come to part B, which is sort of shown on the right side, and this is a more interesting argument, because we have to show now that in general, right, given any set of 5 points, right, that right, any set of 5 points, right, that someone, right, and in fact, right, you can think of it again, a different kind of adversarial game, where the adversary gives you right, a set of d plus 1 points, right, where d plus 1 is 5, right, and right, you can't shatter those, right, and adversary gives another set of 5 points or d plus 1 points, right, and you can't shatter those, right? So right, you have to be able to show this for any set of 5 points, right, and adversary sort of wins in showing that the which dimension is less than d plus 1 if they can show, right, prove that there is no set of d plus 1 points which can be shattered, right? And right, because this is not really we can enumerate, right? Therefore we have to make a general argument, right? So we have discussed that, right? So let us now look at this particular example, right? Let's say someone gives us 5 points, right, in the 2D space, and we will try to make an argument that given any set of 5 points, right, they cannot be shattered by this hypothesis class of axis parallel rectangle, right? And to make this argument, right, right, it is slightly sort of involved, right? Let us look at this particular example shown here, right? So on the right, so let us say your points are x1 1, x2 1, right? So this is the first point, right? x2 2, x2 uh, x1 2, sorry, x2 2, this is the second point, and so on and so forth, right, up to x1 5 and x2 5, right? So this is the fifth point, right? And what we will do here is we will select a set of 4 points from these 5 points, which are, you know, in some sense sort of at extreme of the rectangle that we'll try to cover, right? That will try to show, if we try to construct a rectangle, right, it will not be possible to know, achieve a spatially designed labeling over these 5 points. And what is that labeling is simply, right, let us, you know, choose p1 to be the point which has max value of the first coordinate, which is x1, right? Similarly, let's say p2 is the point which has max value of the second coordinate, which is x2. Similarly, P3, let's say, is the point which has min value of the first coordinate, which is x1, and P4 is the point, right, which has the min value of the second coordinate, which is x2, right? Right, so we sort of go to each of these coordinates and pick its max and min values. Right, there will be, you know, 4 such points that will pick, right? So it may actually be the case that some of these points overlap, but that's okay, right? And right, for simplicity of the argument, I'll make this argument in, you know, slightly easier to think about case where, you know, these 4 points are distinct, right? So once again, what we have done here is we have gone to these 5 points, and among those 5 points we have picked those 4 points where, you know, at least right, where one of the points has the max value of the x1 coordinate, and the second point has the max value of the x2 coordinate, and similarly, you know, the third point has max value, or the min value of the x1 coordinate, and the fourth point has the min value of the x2 coordinate, right? So we pick these 4 points, and in some sense, right, they will sort of be at the extreme, right, in the space of, in the R2 space. And now what we will do is we will, you know, come up with a labeling which assigns positive to these 4 points, right, which have been picked in the above manner, right? So we'll assign P1, P2, P3, P4 to be positive, and we'll assign P5 to be negative, right? And right, and this is shown here in this sort of diagram on the left, right, on the bottom left, right? This P1, P2, P3 and P4, right? So P1 has max x1, P2 has max x2, P3 has min x1, and P4 has min x2, right? And because sort of these are sort of max min points in respective coordinates, right? And since they have to be assigned positive, our rectangle should sort of span all of these points. And by design, right, it has to be the case that P5 is inside or on the rectangle, right? And therefore, right, if all these 4 points are labeled positive, then P5, it must be the case, must also be labeled positive by this rectangle. And right, in some sense that's a contradiction, because we really wanted to get a rectangle, right, where these 4 points are positive, and you know, this fifth point P5 is negative, right? And you can sort of show that a sort of a similar argument will work, right, for any rectangle that we try to construct, because right, in order not to miss any of these 4 points, the rectangle must be, you know, something which sort of covers these 4 points and which will span a space, right, in the 2D space, where P5 must be inside this rectangle, and that will lead to contradiction, right? And again, right, this is sort of a semi-formal argument that we have made, right, to show that there is no rectangle which can sort of achieve this particular labeling in constructed in this manner, right? And note that although the diagram that I've shown on the bottom left is for the specific 4 points, just to, you know, build up the intuition, right? But the argument on the right is actually fairly formal, right? Or it's in fact almost a sort of a complete argument that given any set of 5 points, right, you choose P1, P2, P3, and P4, right, which can be overlapping in some cases, that doesn't matter, right? But you assign write a positive label to the 4 points that you picked and assign negative label to the fifth point, or if there are more than 1 point because of overlap which are remaining, then you assign negative label to any one of those points, right? And this particular labeling cannot be achieved where these 4 points which are picked are assigned positive label, and the remaining point which is assigned the fifth point is assigned negative label, right? And this sort of completes the argument that the VC dimension of this particular hypothesis class, which is sort of the axis parallel rectangles, is uh, because we already showed that it is at least 4, and here we have shown that no set of 5 points can be shattered in the 2D space by this hypothesis class. Therefore, it is less than equal to 5. And having shown that this is greater than equal to 4, the VC dimension is actually exactly equal to 4. Okay. Okay. So let me cover two more examples before I wrap up, this discussion on, looking at various examples of VC dimension and, thinking about how to prove them or how to think about VC dimension, right? So the first example, right, I will state this result without really proving it. It is slightly involved sort of argument with some amount of linear algebra but the result is that VC dimension of a hypothesis class, which is the set of all linear classifiers in Rn, right? Remember that we did this in R2, and we showed that in R2 the VC dimension of this hypothesis class is 3, and you can show, right, with some amount of linear algebra that VC dimension of this hypothesis class, um, which is the set of linear classifiers in Rn, is n plus 1. Right, and as I said, this is slightly involved argument, and maybe right, if you're interested, I can point you to relevant references offline about how to make this argument. But note that our example of R2 and showing that the linear classifiers there have VC dimension of 3 is a special case, because in R2 n is 2, and therefore the VC dimension of this hypothesis class is 3. 3. Okay, and the second sort of example that I want to cover here or state here is that if we consider a set of all polynomials of degree d, right, in R1, right? So these are degree d polynomials in a single variable, right? The VC dimension of this hypothesis class you can show is d plus 1. And what do I really mean by this hypothesis class of which is spanning the set of all polynomials of a given degree d in a single variable is simply, right, we define h theta x. Now x belongs to R because this is in one dimension, is simply right, theta are the parameters of this particular sort of this particular hypothesis, right, and right, h theta of x is simply indicator of theta d x d, theta d minus 1 x d minus 1 theta 1, right, and so on up to theta 1 x plus theta 0 greater than equal to 0, right? So given a set of d plus 1 parameters, we have a specific hypothesis in this hypothesis class which specifies a polynomial, right? And we say a particular point is classified as 1 by this polynomial. If I put that point into the equation of the polynomial, if what comes out is more than or greater than equal to 0, then that point is classified as positive or 1, otherwise it is negative or 0, right? So this is fairly precisely defines this hypothesis class, which consists of degree d polynomials in R1. And right, you can make a very interesting argument, right? Think about it, how to make that argument, right? It can also be thought of as a homework exercise for you, and maybe I will post it right, as part of a practice problem. If I don't, please remind me, but try to prove that the VC dimension of this hypothesis class, which is the set of all polynomials of degree d in R1, is exactly equal to d plus 1, right? And as I said, make sure, or please, I'll encourage you to think about it offline, and remind me if I don't, that I will actually post it as a practice problem on the course website. Thanks. I guess on a lighter side, I said thanks on the last slide, previous slide, but that's probably not yet sort of the end of the lecture, right? We still have two more slides, right, and then we'll be done, right? So we have looked at various examples of how to think about these dimensions, and hopefully, right, they have given you fair amount of intuition, right, how to, right, sort of prove, at least in some simple or moderately difficult cases, right, how to think about this dimension, how to prove that this dimension is a certain number d, right? And as we said that there are two parts to it, that showing that VC dimension is at least d, which typically is slightly easier, and then showing that VC dimension is exactly d, right, which is slightly more sort of it may be slightly more involved argument. Okay, now in this slide I really want to connect everything together, about pack learning, whatever we have discussed in last couple of classes, right? And why is it relevant, this whole theory of this dimension, why is it important, and how does it connect to the case of finite hypothesis, finite sized hypothesis, the case of hypothesis classes which are finite in size, right? And remember that the pack learning bounds, right, that we gave earlier was of the form that probability that for all hypotheses in my hypothesis class, right, this is the expression I'm reading out on the top, probability for all hypotheses in my hypothesis class, the difference between the generalization error and the training error is less than equal to gamma. This probability I would like it to be more than 1 minus delta, right? So these were the kind of bounds that we sort of stated, right, in last couple of lectures, right? And in the case of finite hypothesis classes, right, finite sized hypothesis classes, right, where on the left side I have written it in the slide, right, where let's say the size of the hypothesis class was k, right, we sort of describe the relationship between m, which is the number of examples, right, gamma and delta, which are the parameters in this bound, right, gamma being sort of your error threshold and delta being your sort of right, denoting your confidence, or rather 1 minus delta denoting your confidence, right, I mean depends on how you look at it, but delta and gamma being the parameters, and also the k, which is sort of given to you, right? And we derived various expressions, right, again I'm looking on the left part of the slide, that to be able to achieve a certain bound, right, with given gamma, delta and k, right, m, which is the number of examples, is should be at least 1 by 2 gamma square log 2k by delta, log 2k by delta, right? And we sort of argued about these, right? But I want to make a remark here, right? That in the case of infinite sized hypothesis, right, because k is infinite, right, and these bound will be meaningless, but what can be shown, and which is sort of a whole interesting theory about this topic of learning theory, and VC dimensions and whatnot, that you can sort of replace this argument about m being a certain number of examples, right, and k being a sort of a parameter, right, about which m, the minimum number of examples, is expressed in terms of this k, right. This relationship between these four variables m, k, gamma and delta is expressed in terms of each other, right. In the case of infinite sized hypothesis, right, this k, the role of the k is replaced by the VC dimension, right. So this is really the key intuition, that in the case of finite sized hypothesis, whereas the representational power of a hypothesis class was captured by its size, but in the case of VC dimension, because the size, in the case of infinite size hypothesis, because the size is infinite, right, but we still want to be able to distinguish, let's say, linear classifiers from quadratic classifiers, and therefore the role of the size of the hypothesis class is now taken or substituted by this VC dimension, and these bounds are expressed in terms of these VC dimensions, right. So let us look at this particular bound on the right side, where we are saying that to be able to achieve, right, the pack sort of bound is the same, that to be able to achieve that for all hypotheses, right, the difference between the generalization and the training error is less than equal to gamma, its probability is more than 1 minus delta, right. If the number of examples that I choose now, the expression has changed, is right, of course, will not prove this result, but let me state it, that m should be greater than equal to 1 by gamma into 4 log 2 by delta plus 8d log 13 by gamma, right. So it's sort of a slightly complicated looking expression, but I what I really want to stress here is that if you look at the dependence on d, right, it's actually linear, right. So what we are saying is that right, as VC dimension sort of increases, right, which we saw in the case of going from linear to quadratic classifiers, the VC dimension increased, right. We showed this at least in the case of R2, right, and right. So as the VC dimension sort of increases, right, the number of examples that you will need to achieve a certain sort of pack bound will also go up, right. And then I will make a slight even more interesting argument about this number of the need for number of examples to go up on the next slide. But note that this role of k, the size of the hypothesis class, has been taken up by D for VC dimension. And again, coming back to the left side, right, for the finite case, the dependence of M on K was sort of logarithmic, right? And I won't go into much sort of detail of this argument, but it is connected, right, very intuitively to sort of being able to use log K bits to sort of represent a k-sized hypothesis class. But let's not go there in that argument, right? The main point I want to say is that, you know, this M depends on K, right, in the finite case, right? And as K increases, right, the number of examples that we need also increases, albeit algorithmically, right, to be able to achieve a certain pack bound. But in the case of VC dimension, right, the dependence is sort of similar, right? It is similar in nature, that as you increase the VC, it's monotonic, right? That as you increase the VC dimension, right, the number of examples needed to achieve a certain bound increases, but right, the dependence on VC dimension is sort of linear, right? Right. Whereas in case of the finite, this was sort of logarithmic in K, but both are sort of monotonic. That as K or D increases, the number of examples required to achieve a certain bound also increase. Right. And similarly, right, for gamma on the left side, right, for the finite case, right, gamma was greater than equal to, right, to now expressing gamma in terms of M, K, and delta, right, and again focus on K, right, right, it is logarithmically increasing in terms of K, that as I increase my K, right, the size of the hypothesis class, right, my gamma becomes looser, right? So I, right, the bound that I can give between on the difference between the training and the generalization error also becomes sort of loose, right? Because the error threshold now sort of becomes higher, right? Gamma, right, the lower bound on the gamma increases, right? And on the right side, again, this is, I've not written the exact expression, um, uh, and and I think these are available in Tom Mitchell's book, on machine learning, which is sort of an old book, but I think some of these results are available in that book, and I guess probably other sources also on machine learning. But let me just state this result, that gamma in this case is greater than equal to order, right? This O is order of d by m log m by d plus 1 by m log 1 by delta, right? And again, focusing on the dependence on d, it's sort of linear. Maybe, I mean, there is this log 1 by d factor, but if we sort of ignore that factor, because it sort of grows, right, logarithmically, right, with respect to d, right? So right, mostly, right, it's sort of linear, right? That but definite, right, or in other words, right, to be more precise, right, we can say that because it is d log 1 by d, right, right, this 1 by d, right, m by d factor probably goes down, but overall, right, as d increases, but overall this factor goes up, right, almost I guess linearly, right, in d, right. Therefore, as you increase the VC dimension, the error threshold becomes loose, right. Again, something we saw in the case of finite hypothesis classes, where K increases and error threshold, the lower bound on error threshold increases. And similarly for VC dimension also, right, as we increase D, right, in the case of infinite size hypothesis classes, right, the error bound on gamma, that is the error threshold, also increases, right. That is right, we can sort of now give a looser bound on gamma, right, if VC dimension is more, right, right, for hypothesis classes which have higher VC dimension. And this right, this sort of result that we talked about, right, whether M being sort of more, or gamma being more as we increase the VC dimension, or the size of the hypothesis class, right, to be able to achieve a certain pack bound, is an interesting argument, right, which connects this idea of bias and variance, right, which is a very important concept in machine learning that we'll talk about on the next slide. So just one remark on the previous slide, right? The dependence of gamma on d was of the form order d by m log m by d, and I mean, it may not really be linear. I guess it's sort of a more complicated looking expression, right? So maybe you can ignore my comment, about it being almost linear, but I mean, right, and we can discuss offline about the exact complexity. But the point remains that as sort of the increases, right, the lower bound on gamma increases, right, and which is similar to the case for the finite case, right. And there is a more general argument that you want to make there, right, which is about this bias and variance trade-off, right, which is a very important concept in machine learning. And I guess I don't have enough time to do complete justice to this topic, but I still thought, in remaining about 8 to 10 minutes, I will at least give you broad intuition about, this bias variance trade-off, and right, how does it relate to, things like pack learning bounds and VC dimensions and things we have studied during last 2 3 lectures, right? Let's just revisit the bound, pack learning bound, that we had, probability that for all hypotheses belonging to our hypothesis class, right, the difference between the generalization error and the training error is less than equal to gamma, is that probability is more than 1 minus delta, right? And to be able to achieve this, right, we sort of related the quantities m, k, gamma and delta, or m, d, gamma and delta in the infinite case, and the former being in the finite case, right? And in particular we showed that, right, as the number of as the size of the hypothesis class increases, or in the infinite case as the VC dimension increases, we need more number of examples, right? And this may be, slightly sort of counterintuitive to some of you, because what we are saying is that as you become representationally more powerful, right, we really need more number of examples, right, to be able to achieve a certain pack bound, right? And right, why does that make sense? And in fact, the goal of, next 6 to 8 minutes, right, is to be able to give some intuition about that, right? And this goes into the whole idea of this bias and various trade-off, right, which is a pretty general and important concept in machine learning, right? You see that being applied as sort of an underlying principle, right, when you think about machine learning in general, and then the idea of learnability, right? So let's look at this particular example, right, on the bottom left, right? So this is the case of, this simple class 2 class classification problem, right, in let's say R2, right? And we have these negatives and positives, right? And this green line is sort of your classifier that you construct, right? It is your linear classifier that you might construct over this data, right? And note that, right, these two negatives on the right, which are sort of sitting right next to positives, are a problem, because even on the training data, right, for this data, I guess there is no linear classifier, right, which could separate all these points completely, right? So which means that it is not actually representationally powerful enough, right, to be able to separate these points and achieve the zero training error, right, which is shown on the right side, which is, epsilon hat h of where h is any linear classifier, right? It will not be equal to zero. I guess it will be at least one, or maybe two, right, depending on how exactly you place these points, right? How exactly you place these points, right? But what is interesting is that, right, and this is the notion of bias, right? So the bias in some sense captures, right, your representational capacity in terms of, the best, right, you could do, or your inherent capacity to achieve a certain training error and also generalization error, right, on that given your hypothesis, right? So now what happens, right? Suppose instead of, these linear classifiers, suppose we go to quadratic classifiers, then clearly, right, in this case, right, in this simple example, right, and of course the intuition generalizes to higher dimensions also, and different kinds of hypothesis classes, but in this simple 2D case, right, this red curve is a quadratic classifier, right? And this is like a, a parabola, right, which can actually separate these positives from the negatives, right? And there is indeed a quadratic classifier, right, where there was none such linear classifier which can achieve zero training error on this particular set of examples, right? So which means that this quadratic classifier has higher representational capacity, right, in some sense, right, compared to this linear classifier. And if you think about it, right, this is exactly we captured in VC dimension, that then when we showed that the VC dimension of a quadratic classifier, or the set of quadratic classifiers in 2D, right, is more than, strictly more than the VC dimension of linear classifiers, right? So one point I want to make here, right, is that this VC dimension in fact does capture the inherent capacity, right, of the underlying hypothesis sort of class, and which is also reflected, right, in terms of, its ability to separate, how many points can be separated, right, under all possible different labelings, right? And then we sort of discussed that in earlier slides. But coming back to this whole discussion on bias and variance trade-off, right? So what we can say here is, right, intuitively, right, the linear classifier has higher bias, because right, in this case, because it cannot even represent this underlying concept, where probably the underlying concept is quadratic in nature, right? So it will have the higher bias or non-zero bias, right, to able, right, which is its capacity to represent this underlying pattern in the data, which is quadratic. But the quadratic classifier has a lower bias, right, or it has higher representational capacity, right, which is reflected in its ability to represent this concept and achieve zero training on this particular training example. And note that this is not just about training, because if future data also comes from sort of a quadratic space, then this particular quadratic classifier is expected to do well, right? So this is about the bias, right? But now, right, what is about variance, right? So the variance now says that because right, in this case, this quadratic classifier has sort of higher capacity, right? This also means, right, I guess unfortunately in some sense it has higher variance, which means that it is more susceptible to variations in the specific boundary that is learned, right, because of small variances, right, in the specific examples that you got, right, or because of potentially noise in the data, right? For example, right, and again this is sort of an intuitive argument, right? If some of these right, two negative points on the right side move, right, the quadratic classifier will probably, right, because of its higher capacity, will adjust itself more than what a linear classifier might do, right? And this also connects back to this example, if you remember, I think we had done earlier about, given a set of uh, our points in right, in linear regression, right, you can always find a high enough degree polynomial, I guess, of degree uh, r plus 1, right, which can fit those points perfectly, right? But it may not generalize very well, because it might be fitting noise in the data, right? And similarly here, right, so this is more sort of a subtle argument that this quadratic classifier has higher um, variance, right, which means it is more susceptible to noise in the data, right? And therefore, right, this is exactly reflected in the argument above, that when we say that we uh, have to be able to that to achieve a certain back bound, right, with certain gamma and delta, right, which are respectively error and sort of confidence thresholds, right, we need more number of examples, right, as the capacity of our hypothesis class increases, right? And that makes sense, because this is because exactly because of variance, right, because there is more variance, right? The our classifiers are more susceptible to noise in the data or variations in the training data, right? And therefore, to be able to guarantee that what we observe on training is actually, right, what we might observe on the actual sort of distribution, or when we try to generalize, right, we probably need more examples to be really sure that the difference between the training and the generalization error is less than gamma, right? So this is sort of the intuition about variance. Now, where does bias come in into this picture? Is the whole point that the classes which can achieve lower epsilon hat h, right, can also achieve, hopefully, right, or also do better on future training sets, because of their inherent capacity, right? So there are two things here, right? So one is the ability of a classifier to really right, have low training error, which will hopefully mean also its ability to generalize well, in the sense of being able to represent the underlying pattern, right? So this is sort of the bias, right, in terms of its ability to represent the underlying pattern better, right, which is reflected in the low training error, right? And right, and when I say generalize, right, right, so meaning that in the actual data also, right, it might be able to represent that pattern better, right, which is the case of quadratic classifier. But there is this other trade-off, which is about variance, right, because our training data is finite, right? It is also susceptible to noise, right, which means that it might actually overfit, right, or it might fit noise in the data, right? So one is the capacity to fit the patterns in the data, which is reflected in the bias, right? Lower bias means typically these are higher capacity models, but they also are susceptible to higher variance, right? And therefore there is a sort of a trade-off between this bias and variance. For example, right, a linear classifier has higher bias but lower variance, and quadratic classifier will have lower bias but higher variance. And for a specific problem, what is the right trade-off is really the bias variance trade-off that you need to worry about, and to be able to choose sort of the right sort of classifier for your problem, right? Maybe let me stop this particular discussion here, and I'm happy to discuss it further in question answering session, or offline, or over Piazza. So, right, this brings us to the end of the course, right, as far as the course content is concerned. And right, I wanted to take this opportunity to thank all of you for being patient listeners throughout this class, right, whether it was the first two-third of the course where we could meet physically in the regular classroom setting, right, which was more interactive, or I guess the last one-third or so where we had to meet, right, do these lectures online because of circumstances. But I do hope that the course, right, where we've covered a fair amount of material, right, in machine learning, has really aroused your deeper interest in the subject, and will encourage you to pursue this further, right, whether in terms of application to your own projects, or pursuing research, or in whatever manner that you can think of. Right, the course content has ended, but of course I'll be available for question answers, right, through question answering sessions that we might organize in future, discussion on Piazza, and of course, right, make sure to study well for your exams, which probably will be happening in July, right. So I guess, right, the evaluation component is still left, and make sure to study well for that, and also your assignment for which will be out probably, right, later part of June or July, right, depending on circumstances. Thank you once again.